So we're going to talk about electric potential, but before we do, we're going to go back and review gravitational potential energy, just as a lead-in, okay? So which ball in this picture has greater potential energy and why? Well, if we're looking at these two, I would say the one at the top. It's got greater potential energy. Why? Well, the gravitational potential energy is the mass times the gravitational field constant times the height. Well, we usually say the height is the lowest point, so that would be height 0, which means that this one is higher, so it's got more gravitational potential energy. The next one. Which ball has more potential energy? It's like the same problem. Why? Well, these still have the same mass, okay? And the gravitational field's the same there, so it's just the height that we're worried about, and this one is higher up, because we typically say, again, the bottom is 0. And this one, we've got an even smaller ball. But again, the one at the top is going to have the greater potential energy. Why? It's higher up. Okay? So now, let's take the ball away. There's no ball. There's no mass. So there's no potential energy because we don't have a mass. However, we're going to go ahead and say there's a higher potential up here of some sort. Okay? No energy because there's no mass, but if you were to put a mass here, it's going to have a higher potential energy, okay, with the same mass. So there's a higher potential at this place. Also, notice that the gravitational field is pointing downward, so our higher potential points towards the lower potential. Okay? Now let's go ahead and relate this to electricity. Okay? We've got a capacitor here, a charged plate, positively charged on one, another charged plate, negatively charged on the other side. Okay? We're going to say that this positively charged plate has a higher electric potential. Okay? And electric potential is given by the variable V. And the lower plate has a lower electric potential. Okay? Again, electric potential is given by the variable V. Now, let's look at the electric field in here. The electric field is going to point away from positive and towards negative. So electric field is going to be a nice uniform electric field pointing straight down. Okay? So again, just like the gravitational one, the higher potential points towards the lower potential. When we look at this, the potential on the other page was the gravitational potential energy without the mass. Similarly, we're going to say the electric potential, okay, electric potential, is the electric potential energy, but without the charge, okay? Over here we said that this was without the mass, okay? So we took the mass away. Similarly, we're going to take the charge away, okay? And when we do this, we can go ahead and get a couple of equations because we had two equations for potential energy. One equation that we had for potential energy, electrical potential energy, was negative QED. Well, if we take the charge away, we're going to be left with negative, the electric field, times the distance, is equal to the potential. Okay, the electric potential. Also, we had another equation, okay? We had the electric potential energy was equal to Coulomb's constant times charge 1 times charge 2 divided by the distance, okay? If we go ahead and divide both of these by a charge, we're going to have the electric potential is equal to Coulomb's constant times charge divided by the distance. Okay. Now, we're really more concerned with the change in electric potential, just like we had been concerned with the change in potential energy before. So we want to find the change in potential difference, or the change in potential, which we call the potential difference. Okay, we call the change in potential is the potential difference. Which is also called the voltage. And we will talk more about voltage. All right, so We've got the change in potential. Well, that means it's going to be the change in the distance between the plates. Okay? And then over here, when we talk about the change, we end up with the same equation, but in order to use this, the other location for R is infinity, because then when you divide by infinity, it's 0, so the change is just this minus 0. Okay, let's go ahead and say we put a nice little positive charge up here. Well, you're going to notice if I put a positive charge up here, the positive charge is going to move towards the lower potential. Okay? But if I put a negative charge up here, the negative charge moves towards higher potential. Electric potential is your potential energy per unit charge. So we take the potential energy, divide by the charge, and that gives us our electric potential. So the electric potential is an energy, joules, divided by a charge in coulombs. A joule per coulomb we call a volt. Potential difference is what we're really interested in. So that's the change in potential, okay? And we also call that voltage. Positive charge will move from high to low electric potential. Negative charges will move from low to high electric potential. And then we had this equation, which became these two equations. The change in potential, electric potential, is Coulomb's constant times the charge divided by the distance. Again, the other spot for R has to be infinity. Okay? And then the change in electric potential, or voltage, is equal to the negative electric field times the distance between the two plates.